Good afternoon to everybody. So in this last presentation, I'm going to talk about the future of 3D data, from 3D to 4D scanning. So all the technology that we have presented today and we have discussed it today to capture the 3D body and to process the 3D body scans are using static capture of the body in the well-known A pose. But the bodies are soft and are articulated, and the shape change with the movement, as you can see in this jump, how the soft tissue is deforming during this activity. So 3 years ago, more or less, we decided to develop our own technology to capture the 3D body shape in movement and to work with actual 3D scans of the body shape in different postures and during performing different activities and tasks. This technology has been developed at the IBB, and I would like to mention three of the main properties of this laboratory. One is the speed. This is a high-speed scanner. We can capture up to 180 scans per second, and it was conceived to cover also the sport activities. And the resolution, it's very high. We can acquire to 1 millimeter of resolution, so we can have big details of the body shape. And the technology is scalable and it's based of a modular system that can cover different ranges of scanning areas. And regarding the main characteristics of this technology, I'm going to point out two of them. One is the automatic processing of the scans. So we are gathering many data per second. So it's not possible to process the scan, to fill the holes, and to do it manually. And this processing, it's transforming the mesh and the data in such a way that can be the data useful for many applications that we are going to see later on. And the other important thing is the synchronization with other biometric signals. At the end, the shape is not only the important part of the body for the design of ergonomics products. We need also to manage additional information of the digital human body, the mechanical properties, the movement, and the thermal characteristics. And in order to build this kind of complete digital human model of the body, it's important to gather synchronized information during the activities. So the technology is based on a module, and this module can be replicated to cover a scanning volume. And the module is composed by 3 cameras. 2 of them are infrared cameras and are responsible of the 3D scan. Are responsible of the capturing the 3D shape in the space. And we have an additional RGB camera to capture the texture. So we need also an infrared projector to do this. And as all these modules, all the modules that I cover in the scanning area are synchronized and are connected to a specific workstation to match all the scans, all the visible parts, the captures done by each module by module. And now I'm going to review very fast some of the key points of the processing software because they are important for the applications that we can have later on and we can do later on with the data. The first step of the processing software is to do a dense landmarking and noise filtering that it's done using deep learning networks. This is a classification of the point cloud according to a mesh template. And this is the key step to, at the end, to perform a automatic processing of the point cloud to create the 3D mesh in one step with a very, very good accuracy. This template that we are using, it's always based on a fixed topology, and this fixed topology, it's maintained frame by frame and also between subjects. This is very useful if we want to compare the same points in during all the movement, and if we want to compare those points between subjects. Of course, this topology, it's very useful to have semantic lines and key points that are helping the automatic calculation of measurements. And the processing also, it's using an internal skeleton that it's a key point to connect this technology of 3D shapes with the biomechanic study of the body movement. We are using a model based on 23 joints, and this is according to the International Society of Biomechanics. So this is what to assure the compatibility with all the research done in the biomechanics field. And finally, the texture that we are projecting over the 3D scan is also processed in a way, is also processed in a way that we are maintaining the homology between the 3D mesh and between subjects. So it is very interesting in the case of using this kind of avatars with texture in virtual try-on context, for example. That in that way, we need some elements to guide the composition of other products or a garment with the body. Now I'm going to show you a video of the laboratory during an acquisition. In the right side, you can see the environment of the laboratory and how we are measuring, and in the other side, we have the raw data. And after the acquisition, the processing that I have explained before, produce this kind of results. Mesh without holes, watertight, with the same topology, and with an harmonized color in the texture. And if you can see in this detailed view, it's possible to capture the deformation of the soft tissues in the bust, in the buttock area, in different parts of the body. So now I'm going to review very quick some possible application of this kind of technology. Of course, the laboratory and this technology to capture the body shape movement is quite new. So what we are opening with this technology are new lines of research and new lines to progress, improving the current technology of dynamic anthropometry, biomechanics, simulation, ergonomics, and and also opening new ones that at this moment are not in our hands. Regarding the simulation of clothing and the assessment of clothing, we can use this technology to see how different type of garments are affecting the body shape. And in this case, for example, we can see how it's deforming in one frame, picking only one frame in this case, how is deforming the thigh area, the leg wearing a short, and how is this deformation wearing a longer legging. And this kind of information can be processed and plotted in different ways, like heat map distances and 3D models with the heat map distances. And this is can be useful information during the design process to see in the case of sportwear or compression garment where we need to put more textile or additional stretch, or we need to avoid, for example, some seam in that area. The other application that I was mentioning is the biomechanical analysis. And since we are capturing the 3D body shape and we are capturing in different stages of the movement, we have to obtain values of volume of different body parts that are information that traditionally is used inside the calculations of biomechanical metrics. Traditionally, it's used data from the state of the art because it's not possible to measure a part of the body if we are not cutting this part. So with this information, we can virtually estimate these metrics. And in the case of the biomechanical parameters, how the body, the different segments of the body is movement, and how to compare movement of different body types, different profiles, or to use it in the assessment of performance of a movement in the export context, for example. In the biomechanics world, we are using only a small set of markers distributed along the body, and all the results are very sensible to where are the markers put it, if these markers are located in some area more or less influenced by the vibration of the soft tissue. With this kind of technology, we have we have more points. In this case, we are working with a template of 50,000 points distributed along the body. So we have more data to see what is happening in different parts of the body surface, to select the key markers and to be more precise with the biomechanical analysis. These are some results of a research exploration that we have done this year in order to see how these different groups of markers selected in the site are affecting the patterns of movement, in this case in a jump, and how is this selection is affecting the error when we are calculating the center of the knee joint. And This technology, it's at this moment, it's prepared to capture and to analyze the body shape and how the body shape changes with motion. But an important point and to progress in the next year is to integrate also the product, how the product is influencing the movement, how the product is changing the fitting, it's changing the performance, and at the end to build a to combine all the information capturing with this to create an integrated digital model, as I mentioned before, combining biomechanics, combining the internal skeleton, and combining the muscle activity. And this is some examples of biomechanical modeling done with OpenSim and checking real measurements and simulated measurements. And we have seen that this kind of simulation test beds can be very useful in the future if we can gather the information required to train and to develop these models in a good way or in a good basis. And in the case of the clothing sector, there are many developments to simulate the person, the avatar of the person wearing clothes and doing some movement with the clothes. And now this kind of technology is using a simulation of the body shape that it's not based on actual data, actual scan. There are simulations that in some cases comes from the gaming industry, so are more aesthetic than realistic. And the other thing is how the fitting of the garment it's performing over the 3D body shape. So most of the simulations are considering that the body shape is rigid. The deformation it's only done in the garment, but at the end, depending on the textile, there are some compression of the body. And with this technology, we can create data and we can create information, knowledge, and databases, data to train and to develop this technology with more accuracy and more precision. Yeah, so in this line, one of the important things that we can progress with this kind of technology, it's the creation of data sets for research, data sets for modeling and for prediction. And depending on the application, so we need to add more or less a type of data to these data sets. So the creation of these data sets, I think it's a very important source of information for new deep learning, new technology based on deep learning that can be more realistic than the technology that we have today. We should consider that we are creating many data with this kind of laboratory. As an example, one study done in 2 weeks with 40 subjects and capturing 11 movements with its subjects, it's producing more than 200,000 scans, and each scan it's around 8 million of points. So we have also a challenge managing all this kind of big data. And if I explained it at the beginning, so we can synchronize with this technology with other capturing technology. In this case, we are using RTV cameras, conventional RTV cameras, synchronized with the 3D scans, and the creation of the data sets combining information from both sources are also very potential to the generation of new modeling methods. And that's why, to conclude, I would like to stress the future of R&D that we can open from this technology and from these data sets. And I'm going to mention only three. One is to create new technology to track the movement and with RGB cameras without any markers and in a real situation. So the idea is to move the motion capture laboratory from the lab to the real world using this kind of models and this kind of technology that are more can be more user friendly and less invasive. The other is to generate soft tissue deformation models to animate the avatar in a more realistic way using this kind of data. And this will be very good information for the simulation application based on simulations. And finally, the inference of the 3D models in motion from the RGB video cameras will be something that will be improved. There are some models working now without not very much accuracy, but I think with these data sets, we can improve a lot this kind of methods. That's all from my side. I open now for questions. Here we have my contacts if you are interested in discuss something in more detail in future.
Okay, thank you very much, Sandra. We have two questions. The first one is, which is the type of files that can be exported with scanner?
Yeah, we have different type of files. For the raw point cloud, we are exporting the files in PLY. This is a standard format. For the processed maze, that we are exporting OBJ. It's also a standard format. And in the case of the avatar, the 3D model with the internal skeleton, we are exporting an FBX.
Okay. And the last one is, which is the resolution of the body models captured with MoveQuad 4D?
Yeah, the resolution can be we can configure the resolution from 1 millimeter. It's the minimum, and resolution. And then when we are processing the scan, we are transforming the point cloud into a maze with a topology of 50,000 points. For the applications that we are working on, and based on our experience working with other topologies in the market, we think that it's a very high resolution that covers very well most of the applications.
Okay, so thank you very much, Sandra. We finish this event with this presentation. We appreciate your participation in this event, and see you in the next time. Okay, thank you. Bye-bye.
Bye-bye. Thank you very much for coming.